In this video, we'll discuss gathering, displaying, and interpreting data. Now let's talk about displaying categorical data. There's three different ways that we often display this data. Either using a pictograph, which uses images to represent the number of objects in a category, and you need to include a key that tells exactly what that image represents, because sometimes the image could represent 1 or it could represent a number larger than 1. We could also use a bar chart, which is depicting the relative size of each category as a bar. And we need to make sure that we have axes to help us see where the categories and then what the quantity is of that category. So we need to pay attention also, are we creating horizontal or vertical bars, because both are allowed. Or we could create a pie chart, which is proportionally representing each category to the whole from the data that was collected. So let's look at a set of data of where students are chose their favorite colors, and we're going to represent this in those different formats. For example, if we did a pictograph, maybe we'll use stick figure children to represent the number for each of those categories. So we're going to make the stick figure child represent 2 students. This would mean we'd use 4 of those stick figure children for red, 7 for pink, 9 for blue, and 5 for green. Or we could have created a bar chart. Here you can see we've got the 4 colors labeled at the bottom of our bar chart. The left, our vertical axis, is labeled by 2s since all the numbers are even, and we can easily represent them on the graph. And then each has the bar that goes up to the number that it's representing. And then the pie chart, we can see the proportion of each color to the total of the 50 students that were sampled. And from this, we can see what percent of students chose each of those colors. And in this case, blue was the most chosen color, and so it represents the largest portion of the whole. Now, just like we can display categorical data, we can display numerical data. A dot plot is similar to a pictograph, except that instead of categories, we're using numbers or equal length intervals of numbers. And we use dots often, and they're comparable to the idea of a tally mark. It's just a nice visualization to help us see what's going on. Similar to the bar chart is the histogram. The one distinction is that the bars all touch. There's no gap in between the bars. And again, instead of categories, we have numbers or equal length intervals of numbers. So let's look at an example. Say we have the list of absences for class during March. And these are the different students and how many times they missed during that month. We can then take that data and put it into a dot plot and see that there were 4 students that had 0, 3 that 1. We had 6 at 2, 2 at 3, 2 at 4, 2 at 5, and 1 at 6. Or we could have created a histogram, which again, it's showing the same data, just using bars to help represent each of those different numerical categories. And we can see what does the data do as we look at it from 0 to 6. You can see it kind of slowly gets less and less. Another form of numerical data display that we can use is called the stem and leaf plot. This is very helpful when we're trying to organize multi-digit data. The stems are the parts of the numbers from the tens place and greater. And the leaf is the ones digit. It's important that when we do this and we create our stem and leaf plot, that we make sure that each row is in numerical order. So say we have these grades on the last test. We can see that the lowest grade is a 62. So we're going to go from having stems from 6 all the way up into the 9s for the 90s. So we'll go 6, 7, 8, 9. We'll list each of those. And then in each row, we'll go through and numerically order each of those values. So we want to provide a key to explain what's happening in our stem and leaf. So here, 9 with the /3 means the number 93 on the test. So if we had 6, we have 62, 65, and 68. We've put them in order, and we'll cross them off so that we can have those out of the way. If we go to the 70s, we're going to look for all of our 70s and put them in order. And here that would be 76, 76, 76, and then 78, because that's the numerical order, and we list each of those. The 80s, there's a lot more. And so we have 80, 83, 84, 87, 88, 88, 89, 89. Cross out all those, and then we're left with our 90s. And we've got 90, 91, 93, 94, 98. And this puts all of that data now in a very organized method of seeing how it goes. And it helps us also see a little bit, kind of like the dot graph, how this data lies out. Now we can also use a line graph, which is especially helpful when we're looking at changes over time, because we connect the points of our graph from one to the next, and we can see what that change is happening over time most commonly. For example, say we want to look at U.S. national debt. Here is the amount at each year since 1970 every 5 years. We can then lay out our x-axis as the change in time, and then the y-axis shows the change in the debt in billions of dollars. And you can see it progressed steadily, and recently it's taken off more exponentially. Similarly is a scatter plot. Here we have data points that have a relationship between two kinds of data. And often we're trying to look for some form of trend line or regression line to help us understand that relationship. For example, say that we look at the high school teacher's age and salary in a district, and we recognize that here you can see it's not exactly a straight line, but it's pretty close to one, where teachers that are really young make less money than teachers that are older. So what we could do then is we could create the regression line, which is the line of best fit for this data. And then using a program like Excel, we could determine what that actual line is and how well it fits the data. Now, a lot of this is we're collecting data, trying to understand what it looks like, but also trying to understand what it is telling us and what we can understand from the data we have. When we do this, we want to try to do three different things with our data. We want to be able to read our data, which is explicitly stating facts from our chart or graph. We want to be able to read between the data, where we're comparing and interpreting data within the graph. And then we want to be able to read beyond the data, where we can predict or infer what that data may imply about a similar situation, about the future, or about the population as a whole, because often our data is from a sample. Now let's look at an example here of students' preferences between dogs and cats. Now when we're trying to understand what this data can show us, what it can only show is students' preferences between these two animals. We know nothing about if you included other animals such as fish or birds or rabbits or horses, anything else. It's only going to give us information between these two animals. If we want to read the data, one question could be, how many students prefer dogs? That's literally just reading off the chart. And here we can see that 22 students prefer dogs because our bar goes up to the line of 22. Now, if we're doing a between question, read between the data, we want to compare. The easiest comparison is how many students prefer dogs to cats. Here, we know this is 22, and this one is halfway between 12 and 14, so that would be 13. So 22 minus 13 would give us 9, which means 9 more students prefer dogs to cats. Now, reading beyond the data, we're trying to infer about the population or make some prediction based on this data. So maybe a beyond question can be, which animal do you think is owned the most? Because this is about their preference, not about their ownership. So maybe we say that I would infer more students own dogs since they are preferred more. It may or may not be true unless we go back and get further data, but it is likely a good inference we could make beyond what we know.